We will now discuss an important and interesting phenomenon in nature called resonance. What does the word resonance mean? Have you ever heard somebody saying, yes, what he says resonates with me? What it means is that I tend to agree with him. Now, resonance in nature has the same meaning. Two things seem to agree with each other. Now, what is resonance and when does it happen? Every object has a natural frequency of vibration. What does that mean? Every object has a natural frequency of vibration. In other words, you cannot, if you have a tuning fork here, this tuning fork has a natural frequency. I cannot change the frequency by hitting it hard. If I hit it hard, the amplitude will increase. But its natural frequency will not change. Every object has a natural frequency of vibration. Now, let me see if I can show you some examples. Now, here I have some objects. I'm sure you can see these objects. Now, each of these objects has a natural frequency. You can see this mass, when I hit it, no matter how hard or soft I hit, the frequency will not change. Look at another object. Its frequency will remain the same. That is its natural frequency. Now, look at these beakers. I can produce musical notes on it. You see that? Each of these, look at these two beakers. They are both of the same size, but I have water in one of them. That means its natural frequency, listen, is different from the natural frequency of this. Don't they sound different? They are different. So each object, every object has a natural frequency of vibration. Now, I'm sure you have come across a swing in a park. Now, suppose this is a swing in the park. Now, you keep a child on the swing and give the child a push. And as the child comes back, you give another push. What happens with time? Now, the amplitude of vibration keeps increasing. The child goes higher and higher. Now, this is resonance. Now, I told you resonance means agree. Now, what is agreeing with what here? This pendulum or the swing has a natural frequency. Now, that means when I set it into swinging, its frequency will be a constant. It has a natural frequency. Now, it just came to a stop. Now, every time the swing comes back, I'm going to give it a little force or a little push. And look at this. The frequency of the push and the frequency of the swing are exactly the same. Now here, the two things are agreeing. What are the two things that are agreeing? The frequency, the natural frequency of the swing and the frequency of the push that I give are agreeing. What happens therefore? The amplitude of vibration keeps on increasing, and here you have a resonance. Now, what happens instead of giving that force every time the swing comes back? If I go in between, look at that, I try to give a force here, well, I will stop the swing. It doesn't agree. Now, the force must be given at the end of every swing. Only then will the natural frequency of the swing be equal to the frequency of the push. That means resonance occurs when? When will resonance occur? Can you tell me what is the condition for resonance to occur? In order that resonance may occur, you need to impose a frequency on an object. The frequency of the imposed force must be equal to the natural frequency of that object. Then that object will vibrate with increasing amplitude. You see that? Now, have you ever heard of an opera singer shattering a glass? I have heard about it. I have seen it happen. Now, you know, suppose this is the glass. It has a natural frequency. Suppose I am the opera singer, which I am not. Opera singer can produce frequencies of, in fact, very many frequencies. You know that an opera singer can produce very high frequencies? Is that right? Ah! Okay. If one of the frequencies produced by the opera singer equal to the natural frequency of this glass or beaker, the beaker will vibrate with increasing amplitude, and finally it wouldn't be able to stand it anymore. It will shatter. Now, there are many other examples of resonance in nature where the natural frequency of a vibrating object agrees with an imposed external force. Have you ever heard of a bridge collapsing when a battery of soldiers marching on the bridge? You know that a battery of soldiers marching on a bridge is equivalent to imposing a periodic force on the bridge. You see, there are soldiers going like this, left, right, left, and so on. The bridge is made to move back and forth. Now, this is an external force. If the natural frequency of the bridge equal to the frequency of that external force, the bridge will oscillate back and forth with increasing amplitude. And by the time the soldiers reach the middle of the bridge collapses. In fact, many instances like this happened during World War I. And therefore, during World War II, soldiers, while crossing a bridge, were asked to disperse and not to move in formation. Well, look at the wonderful phenomenon of resonance. So, if I ask you for a definition of resonance, what would that be? What is the definition of resonance? In mechanical system, if a vibrating object is subjected to an external periodic force, where the frequency of that external force equal to the natural frequency of the vibrating object, the object will vibrate with increasing amplitude, and that is what we call the phenomenon of resonance. Well, we have actually seen the phenomenon of resonance. I had demonstrated to you the formation of stationary waves on a stretched string. Do you remember that? Or standing waves. Well, the formation of stationary waves on a stretched string is due to resonance. I'm going to demonstrate that to you one more time. Recall some of the principles we discussed in connection with stationary waves on a stretched string. You can see this stretched string has a natural frequency. From our discussion, you know that the natural frequency, the fundamental frequency we call it, depends on the length of the string. Now, this string is now subjected to an external force. You see, just like the swing was pushed each time it came back, this vibrator is actually applying that external force. Now, if the natural frequency is the same as the frequency of the mechanical vibrator, then the string will vibrate or will resonate with that frequency. When resonance occurs, the string will vibrate with maximum amplitude. Well, I can adjust the frequency so that by the time the energy goes to the fixed end and comes back, a fresh energy is made available. That is what we say the natural frequency and the imposed frequency agree. You see, just the same way the swing comes back, you apply the force. The energy of vibration goes to the end and comes back, the new force is created. Just like you keep pushing this mechanical vibrator, keep generating more energy, by the time the energy gets back, it must be synchronized. You see, the natural frequency of the string must be equal to the frequency of the imposed force. Now, at the moment, the natural frequency is not equal to the frequency of the vibrator. But I'm going to change the frequency of the vibrator and see what happens. All right, I'm changing the frequency. There you got resonance. You see, look at the resonance there. The string is now resonating with the frequency of the imposed force. That means when the energy of vibration travels all the way to the end and back, the fresh energy is created. And there is resonance between the two. Now, this is the fundamental frequency. That means the string will vibrate with a frequency equal to its fundamental frequency. I have the frequency value here I can read is 13 hertz. That means this vibrator, mechanical vibrator, is moving up and down 13 times. And that is a measure of the fundamental frequency of the string. You see, the string will also resonate with twice the frequency here. Is that right? If it resonates with 13 hertz, it should resonate also with 26 hertz. That means by the time the energy goes to the end and comes back, a fresh energy will be available. I'm going to increase the frequency to 26 hertz and see what happens. What I would like you to see is when I increase the frequency, say this is 18 hertz, there is no resonance now. But as I increase it to 26 hertz, look at the resonance. That is the beautiful resonance at 26 hertz. Now this means the frequency of the oscillator or the vibrator is twice the frequency of the string, twice the fundamental frequency. Resonance will also occur if the frequency of the vibrator is 3 times the fundamental. All right? I'm going to make the frequency 3 times the fundamental, about 39. I'm going to increase the frequency. You notice now resonance has disappeared because the natural frequency of the string does not agree with the frequency of the vibrator. Is that right? Okay, I'm going to increase the frequency, see what happens now. All right, the frequency is now getting close to 39, and now you have resonance again. This is the third mode of resonance. The third mode of resonance. Now, can I get it right? I'm trying. There you are. So the third mode of resonance, I can now keep on going to the fourth mode. Let's see if we can get the fourth mode of resonance. All right, that is the fourth mode. Is that right? I think we passed that. There you are. That is the fourth mode of vibration. So this is a beautiful example of resonances in mechanical system. Let's look at this one more time. You can see when the natural frequency of the string equal to the frequency of the external force imposed by the vibrator, the string will resonate, and resonance will occur when the natural frequency of the string is equal to the frequency of the resonator equal to 2 times the frequency of the vibrator, equal to 3 times the frequency of the vibrator, and so on. Well, that's what you actually saw in here. By the time the reflected wave gets back, the second wave is ready to advance. And that is where the agreement occurs. So the energy of the second wave gets reinforced with the reflected wave, and therefore you have the reinforcement and the amplitude increases. You have a big wave, a resonance, is that right? An agreement of frequencies. Now, when this happens, the string is said to resonate with the frequency of the periodic force. In other words, the frequency of the periodic force agrees with the frequency, the natural frequency of the string. That is when resonance occurs. There must be agreement between natural frequency and the external periodic force. All right? That is what resonance is. Let's now look at resonance of air columns. Can air columns resonate? What does that mean? Resonance of air columns. Let's take a look. Air enclosed inside a tube can be made to resonate with an imposed frequency. Now, how can we do that? Let me see if I can show you a couple of examples where air columns can be made to resonate with an external frequency. Now, is there a teenager who has not done this? Now, watch this. This is the cap of a pen, and now, haven't you done this? Well, if you were a high school student and if you wanted to disturb your teacher while teaching, this is what the most common thing among teenagers is. While the teacher is very seriously discussing Newton's law of motion, the student goes, well, the teacher looks back, who did this? I don't know. Nobody knows. Well, it is a good example of resonance of air column. The column of air enclosed inside this tube has a natural frequency. Now, your lips can produce a varieties of frequencies. If one of those frequencies equal to the natural frequency of the air column in here, then the column of air will resonate. You see, that is what you hear, the loud sound. If a frequency does not resonate, no, yes, that particular frequency resonated. And the column of air vibrated with large amplitude, forming stationary waves. Now remember, stationary waves are formed by the formation of nodes and antinodes. So air column inside vibrates, forming nodes and antinodes. All right, let's review a bit on stationary waves. Tell me, what is the distance between two adjacent nodes of a stationary wave? The distance between two nearest nodes is half of a wavelength. Is that right? Yes. So, if you have one complete segment, the length of that one complete segment is 1/2 of a wavelength. We're going to use that in this lesson. Now, I have another tube here. Can you see this? There I have a tube. And a column of air is enclosed in there. And can I make that column of air resonate with an imposed frequency? Well, I can use a tuning fork. Is that right? Vibrate the tuning fork and keep it at the mouth. If the frequency of the tuning fork equal to the natural frequency of the air column, in other words, by the time the first wave energy goes down the length of the tube and returns, you get the new wave produced. That is when resonance occurs. That is, the natural frequency agrees with the frequency of the imposed force. Now, do you hear a loud sound here? I don't hear one, which obviously means there is no resonance. The natural frequency of this air column is not equal to the frequency of the tuning fork. Alright, let's try another tuning fork. There is one. Well, I can hear it's louder than before, but I'm not really satisfied, because if that air column resonates, did you hear this, the resonance of this? Look at this. That's a very loud sound. Now let's try another tuning fork and see if we can get a better result. Well, certainly this is better. So you can now see the air column is now resonating with the frequency of this tuning fork. And the frequency of this tuning fork is written on it, 440 Hertz. So what is the natural frequency of the air column inside the tuning, inside this tube? It is 440 Hertz. That's right. So a column of air can be made to resonate with the frequency of an external force. So a column of air enclosed in a tube has a natural frequency of vibration, and this air column can be made to resonate with the frequency of a tuning fork like this. Set the tuning fork vibrating, and if the natural frequency equal to the frequency of the tuning fork, the air column resonates, producing a loud sound. When resonance occurs, a loud sound can be heard because of the increased amplitude of vibration. Now, when this happens, I told you there are nodes and antinodes formed inside the tube. Now, the particles at the mouth of the tube has the maximum amplitude. You see, at the mouth of the tube, particles cannot be at rest. That means a node can never form at the mouth of the tube. The mouth of the tube will always be an antinode. In the same way, at the fixed end, you cannot have maximum displacement. The fixed end will always be a node. So, if the tube is closed at one end, that closed end will have a node, and the open end will have an antinode. So the open end is an antinode, the closed end is a node. And you can have nodes and antinodes in between depending on the mode of vibration. It can be the mode, maybe the fundamental mode. It can be the higher modes of vibration. What do you call the higher modes of vibration? The harmonics. The higher harmonics or overtones. You see, the vibration of the air column inside a tube is very similar to the vibrations of a stretched string. You have the fundamental, the second harmonic, the third harmonic, and so on. We'll take a look at these as we go on. The higher harmonics of air column can also be made to resonate with the frequency of the periodic force. In other words, the air column will resonate not only a frequency equal to its natural frequency, it will resonate with a frequency equal to twice its natural frequency, 3 times its natural frequency, and so on. That means there are higher harmonics. Let's now talk about a closed tube. A closed tube is the one I just demonstrated. Do you remember the tube I just showed you? The tube I just showed you is this, which is open at one end and closed at the other. So this is a closed tube. Now what is the specialty of a closed tube? A closed tube is closed at one end and open at the other. That means this is the fundamental mode of vibration of a closed tube. Now, in the fundamental mode, you have an antinode at the mouth of the tube, a node at the closed end. The open end will always be an antinode, and the closed end will be a node. In the fundamental mode of vibration, you have a node at the closed end and an antinode at the open end. Now tell me, if this is the fundamental mode of vibration, then how many waves are contained in the full length of the tube? The mouth of the tube is an antinode. The closed end is a node. What is the distance between an antinode and a node? Do you remember that one? Let me just refresh your memory just one more time. Well, if this is a stationary wave where you have node, 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 antinode, antinode, this full length of two loops is one wavelength. You recognize that? One wavelength contains one crest and one trough. That means for a stationary wave, the length of two full segments is a wavelength. That means the distance between two alternate nodes. What will be the distance between two nearest nodes? The length of one full loop or one full segment is half of a wavelength. Tell me, what is the distance between a node and an antinode then? It is a quarter of a wavelength. So inside this tube, in its fundamental mode, what we have is a quarter of a wavelength. The distance between a node and an antinode is a quarter of a wavelength, lambda by 4, and this is the whole length of the tube. So the length of the tube now is a quarter of a wavelength. Let's write that equation. L, the length of the tube, equal to lambda by 4. Therefore, wavelength lambda equal to 4L. In the fundamental mode of vibration, the wavelength of the stationary wave inside the tube is 4 times the length of the tube. Alright, let's say F0 is the frequency of the fundamental. Can you then write an equation of the frequency? Well, frequency equal to wave speed divided by the wavelength. Is that right? If F0 is the frequency of the fundamental and V the speed of sound in air, then F0 equal to V over lambda. And what is lambda equal to? Lambda equal to 4 times the length of the tube. So fundamental frequency of the air column in a closed tube is V over 4L. A very important relation. Alright, let's now look at the next mode of vibration. What will be the next mode of vibration in a closed tube? I don't know whether you can actually see this. Now, in the next mode of vibration, let me just reset my camera a bit. Alright, I want to refocus the camera a bit to show you the picture on the right. There we are. Okay. Now, the second mode of vibration. Remember, the fixed end is a node, the open end is an antinode. So in the next mode of vibration, you can have an antinode and a node inside the tube. Tell me, how many waves are there inside the tube? How many waves? Now, you can see the distance between an antinode and a node is a quarter of a wavelength. That means there is 1/4, 2/4, 3/4 of a wavelength inside the tube now. So what is the relation between the wavelength of the wave inside the tube and the length of the tube? The whole length of the tube now contains 1/4 plus another quarter plus another quarter. There are 3/4 of a wavelength inside the tube now. Therefore, we can say, since the distance between a node and an antinode is a quarter of a lambda, the whole length of the tube now contains 3/4 of a wavelength. That means L, the length of the tube, is 3/4 of a wavelength. Therefore, what is lambda equal to? Lambda equal to 4L divided by 3. Alright, let's now find the frequency of this mode of vibration. The frequency of vibration of this mode is F equal to V over lambda. Our lambda is 4L over 3. And that will be, this 3 will go up. We get that's equal to 3V over 4L. But if you remember, look at this. The fundamental frequency is V over 4L. So this V over 4L is the fundamental frequency. Therefore, in the next mode of vibration, the frequency equal to 3 times the fundamental frequency. That means, you notice one thing. You cannot get twice the fundamental in a closed tube. You get the fundamental frequency. The next mode of vibration in a closed tube is 3 times the fundamental, the third harmonic. In other words, there is no second harmonic in a closed tube. Alright, if you now look at the diagram on the right, this is the third mode of vibration. In the third mode of vibration, of course you have an antinode at the mouth, a node at the closed end, then you have an antinode, node, antinode, node inside. Tell me, how many waves are there inside the length of the tube? You can go like this. The distance between an antinode and a node is a quarter of a wavelength. 1/4, 2/4, 3/4, 4/4, 5/4. There are 5/4 of the wavelength. That means the frequency of this vibration, if you do the same thing as I showed you previously, you will find that it will be 5 times the fundamental. That means if F0 is the fundamental frequency, in the next mode of vibration the frequency will be 3 times the fundamental. And in the next mode, the frequency will be 5 times the fundamental. The next will be 7 times the fundamental, and so on. It means all even harmonics are missing from a closed tube. The fundamental is the first harmonic, and the frequency of the second mode actually is the third harmonic. This is the third harmonic. Only odd multiples of the fundamental are found in the closed tube. All even harmonics are missing. What a pity, is that right? Closed tube does not give us any even harmonic. Let's now look at open tube. What is an open tube? An open tube, by definition, is open at both ends. So, if the tube is open at both ends, look at the fundamental mode of vibration. An antinode has to be at both open ends. An open end cannot have a node. That means a node has to be at the middle. So the fundamental mode of vibration in an open tube has an antinode, a node, and an antinode. Alright? Now, The tube contains how many wavelengths? Can you tell me how many wavelengths are in the tube? The distance between the node and an antinode is a quarter wavelength. So this will be 1/4 wavelength plus 1/4 wavelength will be half of a wavelength. The length of the tube now contains half of a wavelength. So we say L equal to lambda by 2, or lambda equal to 2L. Let's write down an equation for the fundamental frequency of the open tube. The fundamental frequency in an open tube can be written as, alright, F0 equal to V over lambda, and that lambda equal to 2L, and that will be V over 2L. So the frequency of the fundamental is, did you see that? I just changed the screen very quickly. What is the frequency of the fundamental in an open tube? Will be V over 2L. The frequency of the fundamental is V over 2L. Now look at the next mode of vibration, second mode of vibration. There you have 1/4, 2/4, 3/4, 4/4 of a wavelength inside the tube. In other words, the length of the tube equal to one wavelength. Wavelength equal to the length of the tube. Therefore, the frequency of this mode will be, again, frequency is V over lambda, lambda equal to L. So the frequency of the second mode of vibration is V over L. Tell me, what was the frequency of the fundamental? V over 2L. Can you write this in terms of the fundamental? Yes, because V over L is 2 times V over 2L. So the frequency of the second mode is 2 times the fundamental. You see, you have the second harmonic there. Now the frequency of the third mode in a similar way will be the third harmonic, 3F0 and so on. What does that mean? It means in an open tube there are no harmonics missing. Open tube will give you the fundamental, the first harmonic, the second harmonic, the third harmonic, and so on. So if you want to use a tube to construct a musical instrument, for example, which of these tubes will you be preferring? It has to be an open tube. Why don't you want to use a closed tube? Because a closed tube gives you only odd harmonics. Even harmonics are missing. Now, do you know a musical instrument that uses the resonance of air columns inside a tube? There are many musical instruments. A flute, a piccolo, all these are examples using open tube. Now, is there a flute using open tube? Yes. Both ends are open. One end you have the reed where you blow, the other end is open. And you can change the length of the tube. Remember the frequency of the fundamental is V over 2L. L on the denominator. That means as the length increases, the frequency decreases. A very long tube will produce a very low frequency. If you want to produce very high frequency, you go for very short tubes. All right. Let's now talk about musical instruments, of course. Musical instruments make use of this property. All musical instruments, that is wind instrument. What's a wind instrument? A wind instrument makes use of the resonance of air columns to produce musical notes. String instruments uses the resonance of vibrations of strings to produce musical notes. Percussion instruments, that is stretched membranes, like a drum, is using a stretched membrane, and the vibrations of a stretched membrane will produce beautiful musical note. Have you ever heard of African drum playing? Well, I'm very fond of that. Okay, now they all produce fundamental notes and higher harmonics. I told you some time ago that the quality of the note produced by a given musical instrument is due to the particular combinations of the overtones. Overtones are higher harmonics. You see, every musical instrument, along with producing the fundamental frequency, they can also produce higher harmonics. It is the combination of the higher harmonics with the fundamental that gives a musical instrument that unique quality, the quality of the sound, which you can immediately recognize. When you hear a note coming from a guitar, you know it's coming from a guitar. When the same note comes from a piano, you know it is from a piano. When the same note comes from a violin, you know it is from a violin. So, although the same frequency notes are produced by different instruments, they can be traced back to where it came from due to that particular quality. What is the quality due to? Each instrument has that unique combinations of the higher harmonics along with the fundamental. That gives that unique quality. For the same musical note, the combinations of the overtones are different for different instruments, giving rise to that unique quality of the note from each instrument. Now, a church organ. Have you seen a church organ? A church organ is a wind instrument, and it uses many hundreds of, sometimes thousands of pipes. Each pipe is meant to produce one musical note. So a church organ is a wind instrument using individual pipes for each musical note. If you walk into a big cathedral, you can actually see the organ pipes. They are big pipes and small pipes, all beautifully organized. And the church will be reverberating with music from the organ. Now here I have the picture of almost the biggest church organs in the world. You see, the St. Stephen's Cathedral in Passau, Germany, has 1,774 open tubes. Isn't it amazing? That means each of the notes that is produced in the music that is sung in the church come from each of these tubes. Well, let's take a look and see. We can listen to some of these musical instruments. Look at some stringed instruments. What are some of the stringed instruments you have? You have, the first one is violin, and how does it sound? Well, that's how violin sound. How about viola? If you are familiar with music, you know that you can pick out the difference between these two musical sounds. Alright, how about cello? And look at another stringed instrument, bass. Let's now take some look at wind instruments. Well, the flute is the first wind instrument, yeah? Alright, how about the piccolo? And then you have the clarinet. And of course you have the oboe. You have the saxophone. Bill Clinton is one of that. Let's take a look at some brass instruments. There is the French horn. And of course the trumpet. The tuba. There was a weatherman in NBC who used to play around with a tuba. And the trombone. Now finally, let's take a look at some of the percussion instruments. The first one is the cymbals. There you are. How about the snare drum? And the timpani, and finally the bass drum. It doesn't want to produce any sound. Well, you see, we had quite a good look at many of the musical instruments. Alright, let's now look at the resonance tube to measure the velocity of sound in the air. That is an experiment that you will be doing. The resonance of air column to measure the velocity of sound in the air. What I'm going to do is I'm going to demonstrate that to you, and then I will come back and set up the theory. Alright? So give me a second, I will set up the demonstration. Equipment that we will use for the experiment will look like this. Here we have a reservoir that contains some liquid. Well, normally it is water. I put some color so that it will record better. And you have a tube. This is the open tube. Well, the open at the top and closed here. You see, where the liquid is the bottom of the air column. So you have the air column enclosed in here. This is a closed tube. Now, I can increase or decrease the length of the air column by moving the water. You see that? If I move the reservoir out, you can see the water level will fall, the length of the air column will increase. Now, I'm going to keep it back in there. What I'm going to do is, first I'm going to use a clip. Now, here's a clip. I'm going to clip the tube. Now once I clip it, the water will not flow. So I'm going to leave the reservoir down there. And what I'm going to do now is, I'm going to, before I do that, I want to take the level all the way back up. I want to make sure that the level is all the way up there. Alright, let me run the level. The level is now increasing. Alright. And once the level reaches, say, somewhere here, I'm going to stop it. And then I'll take the reservoir down. Okay, I'm going to clip it now. And I'm going to move the reservoir down. And I will open the clip in a controlled manner so that the water level will fall slowly. And what I will do is I will vibrate a tuning fork and keep it at the mouth. And as the length of the air column increases, at a certain length, at a particular length, the natural frequency of the air column will be the same as the frequency of the tuning fork. You will hear the first mode of vibration, the first mode of resonance. Alright, let's do that. I'm going to open the clip to allow the water to fall gently, so that, now listen to this, I'm going to vibrate the tuning fork and keep it there. Now I have actually passed the resonance. So I'm going to do that again to make sure that I don't pass the resonance. Alright, give me some more time. I'm going to take the water level back. Alright. Alright, let the water level go back to the highest level. There it is going. Okay, let's take it all the way to about 10 centimeter. Alright. Okay, and now I'm going to clip it there if I can. Well, there. I'm going to clip it there, and then I'm going to move the reservoir down, and I'm going to make the water fall slowly so that I can control it. There it's falling slowly, and that means the level of the length of the air is increasing. And listen carefully for the sound. Alright? Now, did you hear that loud sound? That is the resonance that happened at 16 centimeter. That is the first mode of vibration. And you know, at the first mode of vibration, you have an antinode at the mouth, a node at the closed end. And now I'm going to let the water flow again so that I can get a second resonance. A second resonance for a larger length. Now tell me, if I got the first resonance at 16 centimeter, where should I expect the next resonance? The next resonance will be another half a wavelength down. So it will be 16 is a quarter of a wavelength. Another half a wavelength will be another 32. That will be 16 plus 32 is about 48. So I'm looking for the second resonance around 48 when I will have an antinode, a node, antinode, and a node. That will be the mode of vibration. Now let's see if we will get a resonance around 48 centimeter. Now I want you to listen to this carefully. There you are. It is exactly at 48 we got the second resonance. Alright, so this is the equipment we use. Let me now set up the theory for you. Here I have a picture of the equipment that I just used. A vibrating tuning fork of frequency F is held at the mouth of a long vertical tube that is filled with water. And water can be drained out of the tube by using this system, as I demonstrated this to you. As the length of the air column increases, as the water level falls, the length of the air column increases, the sound becomes louder. And at the point where the sound is the loudest, stop the water flow when the sound has the maximum loudness. And that is when the air column resonates with the frequency of the tuning fork. That means the fundamental frequency of this column of closed air will be equal to the frequency of the tuning fork. That is what it means at that time. Now this is where the first resonance occurs. Measure the length L1. So in the experiment you will measure that length L1 of the air column. In my experiment we got that as 16 centimeter. Alright, now this will be the mode of vibration at that time. There is an antinode and a node, an antinode at the mouth, a node at the closed end. Now actually in practice, an antinode does not form exactly at the mouth but a little above the mouth. That means we need to apply a correction here. So let us say that the antinode is formed at a distance x from the mouth. That means if the length of the tube you measured is L1, then a quarter of a wavelength is actually L1 plus X. So we will say L1 plus X equal to lambda by 4. This is our first equation. When you get the first resonance, measure the length L1, and if the correction you have to apply for the antinode is X, then L1 plus X is a quarter of the wavelength. Now X is called the end correction, a correction we apply because the antinode is not exactly at the mouth but slightly above it, a distance X above the mouth. Now allow the water to fall again, just like I showed you, and stop the water flow when you hear the next loud sound. That means a longer length of air will now resonate with the frequency of the tuning fork. Now this will be the mode of vibration when you hear the second loud sound. That means the length L2 that you measure will now have an antinode, a node, an antinode, a node. This is the second mode of vibration. And in this case, you can see a quarter of a wavelength plus a quarter of a wavelength plus a quarter. There are 3/4 of a wavelength inside the tube. And what is that equal to? This L2 plus X. So measure the length L2 of the air column. We have now the equation L2 plus X is 3 lambda over 4. We have now two equations, L1 plus X equal to lambda by 4, L2 plus X equal to 3 lambda by 4. We can now use these two equations to obtain an equation for the speed of sound, the velocity of sound in air. Now X can be eliminated. Can you eliminate X from these two equations? Very simple. Subtract equation 1 from equation 2. So subtract equation 1 from equation 2 will be L2 minus L1 plus X minus X equal to 3 lambda by 4 minus lambda by 4. Is that right? So you get L2 minus L1 or L1 plus X minus L2 plus X equal to 3 lambda by 4 minus lambda by 4. Subtract the left hand side from the left hand side and right hand side from the right hand side. What will this be now? You can see L2 minus L1 equal to, this plus X minus X will cancel. We get L2 minus L1 equal to lambda by 2, and therefore lambda equal to the wavelength of the wave inside the tube is 2 times L2 minus L1. Now this is something you measure, so you know the wavelength. Do you know the frequency? Yes, you know the frequency. The frequency is the frequency of the tuning fork. So you know the wavelength, you know the frequency. Can you find the wave speed, wave velocity? V equal to F lambda. That means V, the wave velocity, the velocity of sound in air is 2F times L2 minus L1. And that is a very simple experiment that can be done to measure the speed of sound in air very accurately. In fact, you can get the answer within 0.5% of the actual value. Let's do an example. An organ pipe open at both ends has a fundamental frequency of 400 Hertz. If one end of this is now closed, what will be its fundamental frequency? Do you remember the equation for the fundamental frequency of an open tube? Open tube means open at both ends. The fundamental frequency of an open tube is V over 2L. Whereas the frequency the fundamental frequency of the air column in a closed tube will be V over 4L. Alright? This information is important for us. So what do we know? The fundamental frequency F0 is 400 Hertz for the open pipe. Now, velocity of sound in air is 340 meters per second. For an open pipe, the fundamental frequency is F0 is V over 2L. We know the value of V, we know the value of F0, therefore we can calculate the length of the tube from here. Alright, so length of the tube equal to V divided by 2F0. Alright, use the values of V and F0. Or we can leave it like this because we are going to use this in the second part. What is the second part? This open tube is now made into a closed tube. That means one end of it is now closed. If one end of this now is closed, it now becomes a closed tube. Now, if the fundamental frequency of the closed tube is now F, do you remember the fundamental frequency of the closed tube? It will be F equal to V over 4L. And now, this L, the length of the tube hasn't changed, has it? It's the same tube. Only thing is, it was open in the beginning. We just closed one end. The length hasn't changed. So this length equal to this V over 2F0. So I'm going to replace this L by V over 2F0. That will be V divided by 4 times V over 2F0. Can you simplify that? Now, when you simplify this, the V and V will cancel. 2 cancels with the 4, giving us a 2 on the denominator. This F0 will go up. So this will simplify as F0 over 2. The frequency of the closed tube, the fundamental frequency of the closed tube is half of the fundamental frequency of the corresponding open tube. That will be 400 Hertz divided by 2 equal to 200 Hertz. In other words, if the open tube, the air column inside the open tube will resonate with a tuning fork of 400 Hertz, if one end of it is closed, then the air column inside that tube will resonate with a frequency of 200 Hertz. That's the meaning there. Alright, another one. The shortest pipes used in organs are about 7.5 centimeter. Tell me one more time, will the shortest pipe will give you the highest frequency or the lowest frequency? Well, if you know, an organ pipe, they're all open tubes. What is the frequency of air column in an open tube? V over 2L. L is on the denominator. That means as L increases, the frequency decreases. So shortest tubes will give you the highest frequency. Longest tubes will give you the lowest frequency. Alright, so if you look on a church organ, you got tubes that are very small and tubes that are very long. Each will give you the corresponding frequency. So you have the church organ has a tube that is 7.5 centimeter long. What is the fundamental frequency of this pipe? Right, that's a very simple problem. The organ pipe is an open tube, open on both ends. What is the fundamental frequency of an open pipe? It will be V over 2L, and you know your length, and you know V, the speed of sound in air. What is that? 340 meters per second. Length of the tube is 0.075 meter. Remember to convert units to meters. the organ pipes are open at both ends, and therefore for an open pipe the fundamental frequency is F0 equal to V over 2L. V is 340, L is 0.075. So using those values, we get the fundamental frequency of that pipe is 2267 Hertz. You can see a short tube gives you a very high frequency. Another one. 3 successive resonance frequencies in an organ pipe are 1310, 1834 and 2358 Hertz. Is the pipe closed at one end or open? In other words, is the pipe a closed pipe or an open pipe? What is the fundamental frequency? What is the length of the pipe? Now, do you understand the given information? You are given that these 3 frequencies are 3 successive frequencies that will resonate with the frequency of air column inside a tube. Now, you are not told that this is the fundamental. We don't know the fundamental. This may be some 3rd harmonic or 4th harmonic and so on. The only thing we know is that if this is one frequency that resonates, the next frequency that resonates is this, and the next one is this. These are 3 successive resonant frequencies. You need to figure out these resonances are coming from an open tube or closed tube. Alright, tell me, first of all, what is the difference between an open tube and a closed tube? The major difference is, in an open tube, all the harmonics are present, whereas in a closed tube, only the odd harmonics are present. The fundamental, the 3rd harmonic, the 5th harmonic, and so on. Whereas an open tube gives you all the harmonics. And that is what we're going to use in solving this problem. If the pipe is open, then the following conditions will be satisfied. What are the conditions? Since the higher harmonics are integer multiples of the fundamental, in an open tube, if the fundamental is known, the 2nd harmonic, the 3rd harmonic, that is 2 times the fundamental, 3 times the fundamental, 4 times the fundamental, are all present. That means, if this is an open tube, the difference between these 2 will be the fundamental. Is that right? Similarly, the difference between these 2 will also be the fundamental. So, if this is an open tube, the difference between consecutive resonance must be equal to the fundamental frequency. The difference between the 5th harmonic and the 4th harmonic is the fundamental. The difference between the 10th harmonic and the 9th harmonic is the fundamental. So if the tube is an open tube, the difference between successive resonances must give you the fundamental. Now here, that difference is, let's find the difference. 1834 minus 1310 is 524. 2358 minus 1834 is also the same thing. Now what is the second condition? The second condition is the ratio of any harmonic to the fundamental must be an integer. Is that right? Well, let me show you that. Well, if F0 is the fundamental, then F1 equal to 2 F0. Now F2, let me call it 2nd harmonic. The 3rd harmonic will be 3 F0. The 4th harmonic will be 4 F0. Now what does this mean? It means the ratio of any higher harmonics to the fundamental must be an integer. 2 F0 divided by F0 equal to 2. 3F0 divided by F0 equal to 3. 4F0 divided by F0 equal to 4, and so on. Well, now can we check if this is true in this case? Let's go and have a look at one more time on our fundamental. This is the difference between the successive frequencies. Now that means if this is the fundamental, then if you divide any of these higher harmonics with the fundamental, you must get a whole number, an integer. Then you can conclude that the tube is an open tube. You understand that? If these are the higher harmonics in the open tube, and if this is the fundamental, which is the difference between these two, also the difference between these two. If this is the fundamental and these are the higher harmonics, then you take the ratio of the higher harmonics to the fundamental, then each of these must give you an integer. Now, shall we try? Is that going to be the case? The ratio of any harmonic to the fundamental must be an integer. Here, 1310 divided by 524 is 2.5. It is not an integer. So what is the conclusion? The tube is not an open tube. So therefore this tube is closed at one end. Alright, now you know that the tube is closed at one end, and the difference between the successive resonances is 524 Hertz. In a closed tube, only odd harmonics are present. So therefore, the difference between any two consecutive resonances must be equal to twice the fundamental. Isn't it? In a closed tube, you have, what do you have? You have the fundamental, then you have 3 times the fundamental, then you have 5 times the fundamental, and therefore if you take the difference between any two consecutive resonances, 5F0 minus 3F0 is 2F0. The difference between any two consecutive resonances must be equal to twice the fundamental in a closed tube. Whereas in an open tube, the difference between consecutive resonances equal to the fundamental. You will see the difference there? Alright, so what is the fundamental frequency here? If this is the difference between successive resonances, the fundamental frequency is F0, then 524 is 2F0. Therefore, F0 is 262 Hertz. Look at the argument that we have made in this problem. The given frequencies are therefore the 5th, 7th and the 9th harmonic. The first frequency, 262, is 5 times, 262 times 5 is 1310. 262 times 7 is 1834. 262 times 9 is 2358. So the fundamental frequency is 262. This is the 5th harmonic. This is the 7th harmonic. This is the 9th harmonic, and so on. Alright? For a closed tube, you know the fundamental now is 262 Hertz. And what is the fundamental frequency of a closed tube? F0 equal to V over 4L. We now know F0. We know the value of V. Therefore, we can find the length of that tube. L equal to V over 4F0. And that will be, using the values of V and F0, we get the length of the tube as point. Well, I'm now in a precision